Hello all. Today I will start with chapter 3, that is diodes, and the subtopic PN junction. Right. See, any electronic device has at least one PN junction. For example, diode has how many PN junctions actually? One. Transistor has how many PN junctions? Two. That may be a BJT or FET. The SCR has how many PN junctions actually? 3, right? That means any electronic device has at least one PN junction, right? See, what is a PN junction actually? PN junction is nothing but it is a semiconductor structure. PN junction is nothing but it is a semiconductor structure, okay, which has P-type semiconductor on one side and N-type semiconductor on another side, right? In P-type, the majority charge carriers are holes along with acceptor ions. In N-type, the majority charge carriers are free electrons along with the donor ions. That means the PN junction is said to be electrically neutral or charge neutral, right? Here, what is mean by electrical neutral or charge neutral? See, electrical neutral or charge neutral means the net amount of negative charge is equal to net amount of positive charge, right? See the p-type material, it contains what? Hole along with acceptor. Hole having positive charge, acceptor having negative charge. That means the net amount of positive charge equal to net amount of negative charge means the p-type semiconductor is said to be electrically neutral or charge neutral. Similarly, in N-type, okay, it contains free electron along with donor ion. That means this free electron having negative charge and donor ion having positive charge. That means the net amount of negative charge equal to net amount of positive charge, right? The N-type semiconductor also said to be electrically neutral or charge neutral. That means the total PN junction is said to be electrically neutral or charge neutral, right? Next, what is a junction? Junction is nothing but it is a imaginary plane. What is a junction actually? Junction is nothing but it is a imaginary plane, okay, which separate the p-type semiconductor and n-type semiconductor, right? See, at the junction there is a concentration gradient or concentration change, right? See here how the concentration is changes here actually. See, in p-type the majority are holes, in n-type the minority are holes, right? That means there is a concentration difference. Similarly, in n-type majority are electrons and in p-type minority are electrons. That means there is a concentration difference. Due to this concentration difference or concentration gradient, the holes diffuses into n side and electrons diffuses into p side. At the junction, both electron and hole are recombined each other and disappeared, right? As a result, immobile charge carriers are formed as a region. See, after recombination actually, after disappearance, these immobile charge carriers are formed as a region. This region is called as what actually? Depletion region or spatial region or transition region, right? You know, this depletion region can prevent the flow of charge carriers from P to N and to P, right? Yeah, write down. Write down the notes. Write down. Any electronic device has at least one PN junction. At least one PN junction. Yeah. Next one. Example. Diode has one PN junction. Diode has one PN junction. Transistor has two PN junctions. Transistor has two PN junctions, comma, SCR has three PN junctions. SCR has three PN junctions, right? Next point. PN junction is a semiconductor structure. PN junction is a semiconductor structure which has p-type semiconductor on one side, and n-type semiconductor on another side. N-type semiconductor on another side. right? In P-type, the majority charge carriers are holes, holes, along with acceptor ions, along with acceptor ions. In N-type, the majority charge carriers are free electrons. Majority charge carriers are free electrons, along with donor ions. Along with donor ions. Along with the donor ions. Hence, PN junction is said to be electrically neutral or charge neutral. Electrically neutral or charge neutral. Right. Underlying PN junction is said to be electrically neutral or charge neutral. Right. Next point. Next. Junction is a imaginary plane. Junction is a imaginary plane which separates P-type material and N-type material. P-type material and N-type material. Right. Next point. At the junction, there is a concentration gradient. There is a concentration gradient. Right. Next, due to this concentration gradient, next point, due to this concentration gradient, holes will diffuse into N side. Holes will diffuse into N side, and electrons will diffuse into P side. And electrons will diffuse into P side. Right. Next point. At the junction, both electron hole are recombine each other and disappeared. Yeah. Next point. As a result, this immobile charge formed as a region. This region is called as depletion region or space charge region or transition region. Yeah. Underline depletion region or space charge region or transition region. Right. And next topic. Charge density versus distance plot. Charge density versus distance plot. Right. So now, see here we want to draw the charge density versus distance plot in case of unbiased condition. Unbiased condition or open circuited condition actually. Right. See, unbiased condition is nothing but what without applying any external voltage. Right. See what is the plot of charge density versus distance in case of unbiased conditions. See all of you. First I will start with see outside the depletion region. See outside the depletion region actually what will be the charge density? The charge density value is 0 due to charge neutrality. I already told what is charge neutrality. See, because of the charge neutrality, the charge density value is 0. Charge density is 0. Right. Within a depletion region, what about the charge density? Actually, the charge density is non-zero. Right. Why it is non-zero? Due to immobile charge carriers, that is acceptor ion on P side and donor ion on N side. Right. How to calculate that charge density? See all of you. We know what is the mathematical expression of charge density, rho v equal to Ne, right? Where N is the carrier concentration and E is the charge of electron, right? Here I want to calculate the charge density within a depletion region, right? See, for this Um, for this, consider this region actually first. Here, what is this? This is the depletion region, right? This is also called as depletion width. So this depletion width is called as what actually? WN, right? So WN is nothing but depletion width on N side. And also consider this depletion width, this can be considered as WP, depletion width on P side. Now what is the total depletion width? Actually the total depletion width is indicated with W, right? Now see here, first consider the region if X value lies between 0 and WN, right? So what will be the charge density actually? The charge density is nothing but, okay, N, yeah, carrier concentration. See, if X value lies between 0 and Wn, 0 and Wn actually, which carriers are there? Donor ions are there. That means this N is simply Nd into E. Nd into E. So this is the charge density value if X value lies between 0 and Wn. Similarly, if X lies between minus Wp and 0, what will be the charge density actually? See here, X value lies between minus Wp and 0. This is the 0. What will be the charge actually? Acceptor ions. That means this is Na into E. Yeah, acceptor is denoted with Na into E. But acceptor having which charge? Negative charge. So indicate with a minus sign. Otherwise means outside the depletion region. Outside the depletion region actually what will be the charge density value? 0 because of charge neutrality. Right? Now here I am going to draw the charge density versus distance plot. See here, if X value lies between 0 and Wn, what will be the charge density value? The charge density is nothing but Nd into E. This is Nd into E, right? Similarly, if X value lies between minus Wp and 0, then what will be the charge density actually? The charge density is nothing but minus Na into E. Minus means I think this is the negative portion. See, this is Na into E, right? See here, outside the depletion region, 0. This is the charge density versus distance plot in case of open circuited PN junction, right? And one more point here actually, see the junction actually, at the junction, okay, at the junction, the acceptor concentration is suddenly changes to donor concentration, right? Okay, such a PN junctions are called as what actually? Such a PN junctions are called as abrupt PN junction or step graded junction, right? So here why it is named as abrupt? Abrupt means sudden change. Here concentration is suddenly changes to donor, right? Or the donor is suddenly changes to acceptor. That's why it is named as abrupt. And why it is named as a step graded actually? Graded means change. Step graded means here the concentration is change in terms of step. That's why it is named as step graded junction, right? Yeah, right on the points. Case 1, the first charge density versus distance plot, right? Right on. Outside the depletion region, the charge density is 0. The charge density is 0 because of charge neutrality. Right. Next, within a depletion region, the charge density is non-zero. The charge density is non-zero due to immobile charge carriers. That is acceptor ion on P side and donor ion on N side. Acceptor ion P side, donor ion on N side, right? And it is given by, next point, yeah, copy this one and copy the plot. Yeah, right on a point, right on a point. The junction at which, the junction at which, the junction at which acceptor concentration is suddenly changes to, the acceptor concentration is suddenly changes to donor concentration, donor concentrations. Such a PN junctions are called as, such a PN junctions are called as abrupt PN junction or abrupt PN junction or step graded junction. Step graded junction, right? Underline abrupt or step graded junction, right? And the next topic, electric field versus distance plot. The next one, electric field versus distance plot. Right. So now, if you see what is the electric field versus distance plot in case of PN junction. See, first outside the depletion region. See, outside the depletion region, actually, what will be the electric field value? Actually, 0. Why electric field is 0 outside the depletion region? Because of charge neutrality. Because of charge neutrality. But within a depletion region, electric field is non-zero due to immobile charge. Due to immobile charge, right? How to calculate that electric field, right? See here, this electric field can be calculated with help of Poisson's equation. By using Poisson's equation, Poisson's equation. What is the Poisson's equation actually? D square V by dx square is equal to minus rho V by epsilon. Right? Now integrate on both sides. Integrate on both sides. Now this is dV by dx. dV by dx. So 1 by epsilon integral rho V into dx. Right? Here what is the dV by dx actually? dV by dx is nothing but gradient of potential. Simply gradient of potential is nothing but what? Electric field. Right? Now E equal to minus 1 by epsilon into integral rho V into dx. Here how to calculate electric field actually? By integration of what? Charge density simply. Electric field is calculated by integration of charge density. Right? Now I am going to draw the electric field versus distance plot. See, outside the depletion region actually, what will be the electric field? 0. So within a depletion region actually, what will be the electric fields? Here, integrate this part. If you integrate this part now, then you will get the slope is like this. Right? Here we want to integrate the constant, then we can get the slope is like this with intercept. Similarly, if you integrate this part, so you will get the curve like this. Right. This is what electric field versus distance plot in case of open circuited PN junction. See, what you can observe, what is the observation here actually? See, in case of PN junction, the maximum electric field is present exactly at the junction or at x equal to 0. See, in case of PN junction actually, the maximum electric field is present at the junction. If you consider magnitude, right? Next, write down. Write down. Electric field versus distance plot. Outside the depletion region, electric field is outside the depletion region. Electric field is 0, 0 because of charge neutrality. Because of charge neutrality. Right. Next, within a depletion region, electric field is non-zero. Electric field is non-zero due to immobile charge. Due to immobile charge. Due to immobile charge. Immobile charge. Right. Next, copy these equations and copy the plot. Yeah. Next, write in a point. See, electric field is calculated. Next point. Electric field is calculated by integration of charge density. By integration of charge density. Right. Next point. In a PN junction, electric field is maximum. In a PN junction, electric field is maximum at the junction. At the junction. At the junction, right? Important point. And the next case, next topic. Potential versus distance plot. Potential versus distance plot. Right. So all of you, see, outside the depletion region, actually what will be the potential, right? Here the potential is constant. Why potential is constant outside the depletion region? Actually because of charge neutrality. Because of charge neutrality. Here in case of P side, the potential is constant because of charge neutrality, right? Similarly, in case of N side, the potential is constant because of charge neutrality. But within a depletion region, actually the potential is varies. The potential is varies like this. This is the potential versus distance plot. See here within a depletion region, actually the potential is varies because of what? Actually immobile charge carriers, right? Okay, so this potential is called as what? Actually this potential is called as built-in potential. Built-in potential or barrier potential or diffusion potential. Diffusion potential, right? And it is denoted with V0. Barrier potential or built-in potential or diffusion potential, it is denoted with what? Actually V0, right? See, why it is named as built-in potential? Actually because see, without applying any external voltage, here the some potential is induced. That's why it is named as built-in potential. And why it is named as barrier potential? Actually, see, because of this depletion region, actually no charge carriers are moving from P to N as well as N to P. That means simply this depletion region will act like a barrier. That's why it is also called as barrier potential. Why it is named as diffusion potential? Actually, see here this depletion region is formed because of which process? Diffusion process. That's why it is also named as diffusion potential, right? Yeah, copy. Next, potential versus distance plot. Write down. Outside the depletion region, the potential is constant. Potential is constant because of charge neutrality. Right. Next one. Within a depletion region, within a depletion region. Potential is linearly varies. Linearly varies. Right. Linearly varies. Right. Copy this plot. Potential versus distance plot. Yeah. Next, write a point. Due to immobile charge carriers within a depletion region, potential is induced. This potential is called as built-in potential or barrier potential or diffusion potential Underline built-in potential, barrier potential, diffusion potential in bracket V naught. Yeah. Next, I will also plot the energy versus distance plot of a PN junction. See, that is very, very important actually, because see, when we apply any voltage to electronic device actually, so what is the energy changes inside the electronic device that we want to observe actually, right? Here to draw the potential energy versus distance plot actually, tell me, in case of PN junction actually, how it will varies actually. See, in case of PN junction in open circuit condition actually, the energy is varies like this, means the direction of the potential is what actually? The direction of the potential is positive to negative, right? Then how energy is varies actually? The energy is varies from right, negative to positive. That means both will be opposite. See, if the potential is varies from, means the direction of the potential is positive to negative, then the direction of the energy is negative to positive. But that means both will be opposite, right? Now here I am drawing energy versus distance plot in case of unbiased PN junction. See, like this. See, here also energy is constant because of charge neutrality, but within a depletion region actually the energy is varies. How it will varies actually? It will varies from negative to positive. Potential is varies from positive to negative, but the energy is varies from negative to positive. This is the energy versus distance plot, right? Copy. Energy versus distance plot. Next topic, calculation of built-in potential. Built-in potential. See, to calculate the built-in potential of a PN junction in open circuited condition actually, see, consider a PN junction. In open circuited condition for which current through this PN junction is 0. Right. See here. See, to calculate the built-in potential actually, consider a PN junction actually in open circuit condition actually for which the current through this PN junction is 0. Current through the PN junction is 0 means both JP is 0 and the JN will also 0. JP means current due to holes and JN means current due to free electrons, right? You know, in case of current due to holes or current due to free electrons due to two mechanisms actually, that is drift as well as diffusion. That means the Jp total is simply Jp drift plus Jp diffusion, which is equal to 0, because here we are in open circuit condition, right? Similarly, Jn also, Jn drift plus Jn diffusion, right? See, what will be the Jp drift actually? Jp drift is nothing but P into E into mu P into E, right? And what is the Jp diffusion actually? Jp diffusion is nothing but minus E into dP into dP by dx, which is equal to 0, right? Now from this, so P into E into mu P into E equal to E into dP into dP by dx. What is the electric field in terms of potential actually? That is minus dV by dx. Gradient of potential is nothing but electric field, right? So which is equal to E into dP into dP by dx, right? Here E cancel and dx cancel, right? So from this, P into mu P into minus dV equal to dP into dP by dx, right? Now from this, P into dV equal to minus dP by mu P into dP. Sorry, here already dx is cancelled. Here dx is cancelled, right? Yeah. See, what is the dP by mu P actually? With help of Einstein equation actually, Vt. Vt means thermal voltage, right? Now dV equal to minus Vt into dP by P, right? Now integrating on both sides. Integrate on both sides. Now V0 equal to minus Vt into integral dP by P, right? See here, we want to calculate the built-in potential, right? Built-in potential means this one actually. Here how the concentration is varies actually, the concentration is varies from PP0 to PN0. Actually, what is this PP0? This PP0 is nothing but, whole concentration in P region, right? And what about the PN0? Whole concentration in N region. Whole concentration in N region, right? Now this is PP0 and this is PN0 limits. If the concentration is varies from PP0 to PN0. Now V0 equal to minus Vt into, what is the integration of 1 by P actually? Ln of P. Limits PN0 and PP0. Now V0 equal to Vt into Ln of PP0 by PN0, right? But what is PP0 actually? PP0 is nothing but whole concentration in P region, that's simply a acceptor concentration, right? And what about the PN0 actually? PN0 is nothing but whole concentration in N region, that means minority carrier concentration, right? Right. This PN0 is nothing but Ni square by Nd, right? Now what is the V0 here? V0 is nothing but Vt into Ln of, this is Na by Ni square by Nd, which is equal to V0 equal to Vt into Ln of Na into Nd by Ni square. Yeah, this is the equation of built-in potential in open circuited condition actually, right? Copy. Yeah, completed. Yeah, next point, listen actually. See, in case of PN junction actually the built-in potential depends on what? So in case of PN junction actually the built-in potential will depends on both carrier concentration as well as intrinsic concentration. It will depends on both carrier concentration as well as intrinsic concentration. And also it depends on temperature also actually. See here how it will depends on temperature actually. See here from this equation, what is the relation between potential and temperature? Actually both will be directly proportional, right? So Vt is nothing but thermal voltage. What is the Vt value? Vt is nothing but Kt by Q, right? That means both are directly here. But actually in case of PN junction the two mechanisms are involving actually. See here the two mechanisms actually. The first mechanism with respect to formula. Mechanism 1, the first one. The first one is mechanism 1. See, as temperature is increased, what will be the built-in potential actually? The built-in potential is increased with respect to this formula, right? One more mechanism is there actually. So mechanism 2 actually. See, as temperature is increased, what happened in case of semiconductor device? You know, intrinsic concentration is increased. Intrinsic concentration is increased. Just now I told this built-in potential also depends on what? Intrinsic concentration, right? As temperature is increased, intrinsic concentration is increased. If intrinsic concentration increases means what about the built-in potential actually? The built-in potential is decreases, right? Now here with respect to mechanism 1, as temperature increases, built-in potential is increases, and mechanism 2, as temperature increases, built-in potential is decreases. That means which mechanism is dominating actually? You know, the both mechanisms at a time is not possible, right? So which mechanism is dominating? The mechanism 2 will dominate mechanism 1 because this is a square term. This is only power directly proportional. This is inversely proportional. That too, this is a square term, right? So this mechanism 2 will dominate the mechanism 1. That means, so finally, what is the conclusion actually? As temperature is increased, what will be the built-in potential actually? The built-in potential is decreases in case of PN junction. Very, very, very important point, right? Copy this point actually, very, very important point. Right down. In a PN junction, comma, the built-in potential depends on both carrier concentration and intrinsic concentration. Intrinsic concentration. Intrinsic concentration. Intrinsic concentration, right? Yeah. Next, heading temperature effect on V naught. Next heading temperature effect on V naught. Right. Copy these two mechanisms and write on the final conclusion. Right. Completed. And the one more point actually. See, in case of silicon, if it is a silicon PN junction, what will be the built-in potential value? The built-in potential value is 0.7. If it is a germanium PN junction, actually, that means what will be the built-in potential? 0.3. V naught is 0.3. Yeah, copy. For silicon, V naught equal to 0.7. For germanium, V naught equal to 0.3.